And this time we have Magnus Jahre. He is an associate professor at the Department of Computer Science at NTNU. And he will talk about how quantum computers fit in the trend of increasingly heterogeneous computer systems.
Okay, thank you for that introduction. So my plan today is to talk about how kind of the generic trends within computer architecture has led to, which is conventional computer architecture is a very conservative field, but there are a couple of trends that means that the field has over the last, say, 10 years become a lot less conservative. So the title is Architecting Quantum Computers, but it is really more general than, like, the things that I say mostly apply to any computer system. But then since we are mainly concerned with quantum computers, then I will use that as a more specific example. So it's not looking good for computers in general. So the first item of bad news is that performance isn't scaling very well. This is the classical scaling plot by Hennessy and Patterson from their textbook, and it shows that from '86 to about 2003, we had an exponential increase in computer architecture performance, in single core performance. But later than that, the performance improvement has stagnated, and now over the last few years, single core performance isn't improving at all. So we need to do something differently. The other side of bad news isn't super visible in this plot. So this is a plot of transistors per chip over years. And we can see that it's nice and linear and that the y-axis is exponential. But over here in the top hand corner, if you can see my mouse, you can see that the signs are starting to slag off from this nice and linear curve. And if you look behind the numbers, it's even worse. So the new factories that are going to make the next leap in technology they are delayed and delayed yet again. So this has started to slow, and it's pretty much consensus that Moore's law, as we know it, is dead. And this is a problem because the area of the chips that we can build is practically constant. Because if you could think that, okay, we can't scale the transistors, so let's just make the chips larger and we can scale in that way. But that doesn't work because then you have poor yield. So most of many of the chips that you produce don't have the desired functionality. So to work around that, people have started to do something called multi-chip modules, where you put something called an interposer, and then you make individual chips, in this case, processor cores and memory. You make these individually, and then you glue them together on top of this interposer, and hence you can continue scaling. Meaning that even if Moore's law has ended and technology isn't scaling, we can still glue more of the individually processed chips together. So this means that we are not going to run out of resources in the short term. But of course, also this will have its limit eventually. There's also a couple of opportunities. So if you look at hardware from the point of view of software, it looks roughly like this thing. This is an Intel 8086. It's from '78. It executes one instruction per cycle. It accesses memory in one cycle. And this is kind of what once we see, this is the model that we worked really hard from the hardware side to expose to software. What you actually program is this thing. And this isn't entirely one-to-one with the chip on the left, because there's also a GPU on here. But it's this massively complex thing that does it does a lot of things. What it does not do a lot of is compute. So if we look at roughly the units that do computation on this thing, those are the black boxes. So out of all of the area that we have, all of the resources that we have on this chip, like a very limited amount perform actual computation. And the rest of it is the overhead of moving instructions around. Software is also inefficient, but for a different reason. So from the hardware, we say, okay, we have our instruction set. This is the functions that we expose to software. On top of that, we put the operating system. On top of that, we put language runtime. On top of that, we put the application. And depending on how complex you want to make this, then you will get a lot of abstraction layers. And as you go up the stack, the systems become more programmable. So you can get more done with less programming, but typically also efficiency decreases. So there's this fundamental trade-off between efficiency and programmability. And it's kind of somewhat imprecisely put into Worth's law, which is that software, the observation that software is getting slower more rapidly than hardware is getting faster. So that's a bit depressing. But at the same time, software, like developing software, takes a long time and people get it wrong a lot of the time. So this is by no means a problem that is solved by abstraction levels. So from this, we have the observation, I think the key takeaway from this analysis is that we've had a good run with technology scaling, and we've used it to build more programmable, but less efficient computer systems. And meaning that going forward, since technology scaling isn't going to help us anymore, we need to do something different. And the ambition should be to make computers that are both efficient and programmable. And to do this, I think we need to take a step back. So what's really this computation thing? And this is where the relevance to quantum computing kind of comes in again. And so basically, you can look at a computer at two levels. At the abstract level, you have some input that you somehow put into your machine. You perform some computation on it, and you get the output that you observe. In physical terms, this means that the input is something that you impose on the system so that it achieves a desired state. Then you perform some computation. This is a state transformation. So it goes from one state to another state, and then you read the state back. And this is what computers do. The regular state in a regular computer, the state is in memory, and then the computation is the state transformation is performed by a sequence of instructions, and then you read out the memory state at the end of it. So that it's natural to think that there are a lot of ways to physically perform this process. And what we're looking to do in conventional computer architecture now is to attack kind of the main source of inefficiency, which is really the general purpose ambition of conventional computers. So we want to build. The general purpose ambition is that for any program that you write, the computer is going to perform pretty well. It's not going to be really bad, and most likely, since it's general, it's not going to be really good either. And by relaxing this, we relax this ambition by doing specialization. And specialization means that the computer is still generic in the sense that it can compute any computable function, but it is much better at certain computations, so certain state transformations than others. And then we try to figure out for certain applications or application domains that are important. In this case, like a recent example, or these days, everybody's doing machine learning accelerators. So then they're taking the functions, the computations that are typical in certain classes of machine learning systems, and they're making special purpose hardware, or hardware that fits really well to this class. And then to retain programmability, you normally try to express these computations through something called a domain-specific language. And the problem with using a general purpose programming language is that, well, again, it's general purpose. And it's also typically tailored to the kind of this instruction paradigm. And as you move down the abstraction layers, you lose information. And this means that you're limited to lower level optimizations, whereas maybe you could do a lot more powerful things if you retained a higher, like you were able to retain some higher level information. And interestingly, I think this specialization paradigm works because we still have the conventional general purpose processor. So the general purpose processor is really good at the things that are just difficult to get to run well. So if you have lots of branches, lots of indirect memory accesses, lots of data dependent stuff, well, the processor is a regular processor is quite good, and these are things that are typically difficult to specialize for. So from this perspective, you can look at quantum computers as yet another accelerator. And in this view, so I took this figure from Ding and Chong that wrote it's a recent book about kind of computer architecture research in the direction of quantum computers. And it's a bit similar to what you've seen. So there's the CPU that does kind of the management functions, and then there's actually quite a lot of that going around, and then the actual quantum computation is a relatively small part. On the other hand, quantum computers are definitely not just another accelerator in the sense that they have the potential to be more than polynomially faster than a probabilistic Turing machine. So their performance potential is much greater. So it is fundamentally something different. But then there was this thing about programmability, right? We want to be able to tell the machine to do what we want it to do. And Ding and Chong, they claim that like quantum computers today is roughly at the stage where regular computer systems were in the 1950s, meaning that you have the algorithms at the top level, and you have the devices at the bottom level, and then you have this bunch of stuff that needs to be done in the middle, but it's not kind of cleanly abstracted into layers, and like you're not able to hide away the unimportant functionality and expose the important functionality. So that's definitely something that one would need to work on. And then to be a bit more specific, I found this recent paper in Nature where they describe a recent quantum computer. And as far as I could see from like my computer architecture classes on, I think that the novelty in terms of the computer architect, like the stack there, was that they inserted a domain specific language. So they added the code that they used. And then this code over here communicate, like under the hood, lots of things happen, and they are able to compute something. Again, it's the same principle. It's kind of the same observation. There's a very limited part of the system that actually does computation. Like there's a lot of stuff that needs to happen for this computation to happen. And there's also, I think, a lot that can be done on the programmability level. in the sense that this, to me, this looks a bit like what we write when we specify hardware. So it looks like a hardware description language where you're at the level of you're specifying the gates and how they should be connected to each other. But it's definitely interesting in the sense that the work is going on in this direction. Another classic part of computer architecture is something called Amdahls Law, meaning which tells you that basically the thing that you don't improve will eventually dominate performance. So if you have a system where you multiply for 80 seconds out of 100 seconds, and then you want to make a multiplier that's going to give you a 5x speed up overall, well, you will find that in this particular case, that would mean that you would need to infinitely speed up multiply, because the 20 seconds that you do other stuff will dominate execution time. And again, coming back to quantum computing, as the devices become more powerful, as one would presume that they would, the efficiency of the other abstraction levels becomes relatively more important. And this kind of comes down to one of the more or less fundamental observations with respect to specialization, and it is that eventually, and most accelerators end up being memory bound. So it is the transfer of the input data and the output data that becomes the key bottleneck. And so, and that's interesting, right? Because that's also something that we like. That's problems that we like to work on. So to summarize, I think quantum computers, they're a good fit for the kind of the trends that we see in conventional computer architecture. They have a set of unique capabilities. These unique capabilities also make them highly susceptible to Amdahls Law. So it's going to be super interesting to see how that fans out. There's definitely a lot of research that can be done from this perspective, but it's one of those things that are really difficult to do, because first of all, you need access to the expertise, like people that actually understand how these quantum phenomena works, where I think this center is a good opportunity. And then computer architecture is also a very quantitative field. So we need to be able to implement things and measure, which requires infrastructure, either in the form of experiments on real hardware or simulators. And that was, I think, roughly what I was planning to say. So if there are any questions, I would be happy to try to answer.
I had a question from the beginning there when you talked about the development it was on performance.
Slide 2.
Yeah, So a more general thing, which has probably, is that computation today takes a significant amount of world's energy consumption.
Mm-hmm.
So not zero. So global computation is more or less energy consumption bound on a global scale. I don't know if it's any comments on that.
That's entirely correct. And I could talk about that for forever, more or less. So it's super interesting because there are two things that limit computer systems. It's energy and it's power. And interestingly, energy is the main limiter for the smallest systems, because they are limited by, here we're talking like systems that do energy harvesting or systems where replacing batteries are costly or impossible due to the kind of the domain that they're deployed in. So they're obviously energy limited. And then at the supercomputer level or the data center level, you're also energy limited because the total cost of ownership is dominated by your energy bill. So energy efficiency is super important. For the mid-range, we're more concerned about power because it's the rate at which you dissipate energy that determines how big your cooling system needs to be. And if you want exotic cooling systems, they take space and they cost money. If we're talking more fundamentally, actually, in a computer system, the actual computation is rather cheap in terms of energy, but the data management is expensive. And if you look at if I can get to the die photo, so the computation goes on in here, right? But for the data and the instructions to go here, it comes in here over the memory controller. Then it goes here through the ring. Then it goes into the L3 cache. Then it goes through the L2 cache, and then there's probably an L1 cache somewhere. And then it enters into the processor core. And then the processor core works really hard to figure out which of these instructions can we run in parallel. And so it has like a couple of hundred instructions in flight at any given time, ideally. So yes, energy is a limiter for sure.
So if you think in terms of quantum computer, one is the speed, but it's the representation power, so that you could do a certain computation with much less memory. That would maybe be a more important point on that large thing.
Can I just ask, why can you do a computation with less memory capacity?
Certain computations, so you can represent the things with qubits, and then that's exponentially depending on the algorithm, of course, but generally they need a lot less qubits than you need bits to do the same thing.
There was actually an article, I don't remember it off the top of my head, but they showed that they did a quantum computation, and if you wanted to do the same computation classically, it would not be much faster, but it would consume, I don't remember, 1,000 times more energy. So there is an argument to be made that maybe quantum computers, at least in the beginning, might not have a speed advantage, but actually an energy advantage.
Yeah, but this is assuming that you have encoded the state already, right? Because I think this is so. So memory is two things here. Memory is both the task of taking your input and then moving it into the machine in some way, like encoding the state, and then transforming the state. So I think like once you have the data in the quantum computer, like in the quantum representation or whatever you like one should call that, then I think then I think those kinds of arguments apply. But then you need to get there somehow.
Yes, and there's this concept of quantum RAM, where, for instance, for some machine learning tasks, not all of them, but some of them, where you need to load a lot of data, you would have the bottleneck to input the data. So you could imagine quantum RAM that makes this efficient. But there are other types of computations where you have little input, but the computation sort of inside blows up. And for this, then I think the input, the data management isn't the problem anymore.
Sorry, I think you misunderstood my question. I mean, for when we do standard computation, that kind of me and Magnus is kind of doing in very different way. But anyway, when you have a certain problem, you have a requirement to solve the problem in memory capacity. And that's kind of a theoretical thing related to the Turing machine, actually. It's a kind of theoretical view of what this problem require. And then you transfer this to a quantum world, then you kind of get the same. To solve this problem, you need some memory capacity. If it's a quantum memory capacity or a standard array, it doesn't really matter. That was kind of my point. Memory capacity is a requirement for any kind of computational problem. Or is I totally off?
One remark that's maybe related. I don't think you can use a quantum memory as a memory because it's huge because of the dimensions of the Hilbert space, but it's not accessible in any way. You can only use it internally in a quantum computer to speed up things that benefit from parallelism. I mean, there's no way you can use a quantum RAM to just store information, classical information, and get it back later when you need it in an efficient way. As far as
No, that was not what I meant. I mean, if you want to solve the problem, you need some memory depth, some capacity to solve the problem. And then how does the actual physical quantum memory, or whatever you want to call it, grow? And what is the, for instance, the energy relation between keeping this memory actually accessible for the quantum world? How cold must it be?
Yeah.
What kind of energy do you actually need to keep the qubits in place long enough to be able to compute the problem, and that kind of thing? Because I guess the memory capacity, if you think of a certain problem or class of problem, is not going away, as I understand it.
I guess it depends a bit on the technology. If you use photonic quantum computers, I don't think you need to cool it down. But there are certain problems that aren't solved with that technology, so I don't know.
Yeah, I don't know.
Yeah, I'm not sure if I have a good answer for this in general, but the point is probably that a quantum algorithm, the statement of the problem, you cannot get away with that. But during the algorithm, you may not need to increase, have more qubits, have much less qubits than you need in a classical algorithm, where the intermediate calculations may need a lot of memory.
Yes.
So it has to depend that this is the point. It doesn't mean that all kinds of computation has that property.
Exactly. Can I ask a question, Magnus?
For sure, yeah.
About your talk. So did I understand correctly that you're basically hinting at, you say, well, we hit this plateau in all the Moore's laws and so, and maybe there's a way to use quantum computations for specific tasks to just accelerate the whole the whole thing as a whole, right? Was that sort of the selling point? Maybe let me ask my question, because then you run into, if I want my desktop in 20 years to be faster than this, and it's going to be assisted with quantum computing elements, they only work efficiently for very specific tasks. I was just wondering how much, and that's an honest question, how much of what's going on inside my own computer actually would benefit from a quantum computer? I mean, it's not that often that it needs to factorize a prime number or so, or is it?
I think that's a great question. And I don't think we've even tried to attempt to answer that question in the context of quantum computers yet. Like just for regular acceleration, like very near-term incremental acceleration, we don't really understand which parts of applications benefit from acceleration. There's some, like, it should be decently parallel, it should compute in a lot of data, you should have some, like, shouldn't synchronize too much, etc. So kind of the constraints. But how that is mapped onto physical compute substrates in a somewhat generic way, I think that's a big unknown.
Mm-hmm.
Machine learning is a good one, though.
Yeah.
But is machine learning a good example for quantum computers?
Good example. Sorry, what do you mean?
I'm just thinking. Okay, I liked. Can you move a few slides ahead, Magnus? I will say stop. More. One of your pictures. Yeah, here, for instance. There. One back. Or one. This one, yes. Machine learning is kind of an awful lot of data. And in this figure here, then you need to put all of these data, often gigabytes or terabytes of data, to be kind of go through this quantum chip. So you need to feed it. And again, as I understand it, one of the main problem is that the computer cannot be faster than the time it takes to set it up. So if you wants to go through a trillion images in a kind of machine learning fashion, then you need to set up each image in the quantum world in a way. But can you set all of them up in the same time?
Isn't this,
or anyway, you have to put them in there somehow. And then you are kind of back to our fundamental boring problem of memory bandwidth in a way, or memory latency.
But isn't this comment more about quantum computers in general than about this specific diagram, or this?
Yeah, it's about. It was more just like an example of is machine learning a good example for where quantum computers really could do great.
But I guess it depends a bit also, because I think the prime example or one of the examples that they use is this support vector machine. Yeah. And there the input isn't that big. And then you don't lose this advantage of, I mean, it's the figure, the equation that you had 80 over n plus 20. So the 20 is sort of the input of the data. So any speed up you gain in the algorithm will be eaten up by the exponentially slow input thing. So, but I think there was Seth Lloyd that offered Google to give him money to build some quantum RAM, but they did not. They didn't bite. I think because that's if you can build it, then it sort of circumvents this problem. But I think most experts say that this will not be able. You will not be able to build it.
I'm probably way off. I was just thinking that the kind of killer thing to do is something that requires little data, but extreme amount of computation.
Yeah, like quantum chemistry. I think that,
yes,
that might be the first, like quantum mechanical systems. In my opinion, will be the first application where you might get something going.
Yeah, I also think so.